Okay, so let's start. So thank you everyone for joining again this week. So first off, today we're very happy to have Lina Chen, Nanjing University, tell us about segment inequality and almost rigidity structures for integral Ricci curvature. So please start.
Okay, thanks for inviting me, and it's my pleasure to present my work here. So my title is segment inequality and almost rigidity structures for integral Ricci curvature, and I will discuss it in the following 4 parts. And first, let's say what is integral Ricci curvature. As I know, Galot has given some volume properties about manifolds with integral Ricci curvature in 1988. And the most well-known application of the integral Ricci curvature may be Tian and Zhang's regularity of Kähler final Ricci flow. Maybe I'm not very familiar with their work, but I know it is a very good application of this integral Ricci curvature. Let's say what is integral Ricci curvature. Consider a complete remaining manifold M, and let zo h be a function which amount the Ricci curvature that lying below n-1h, and define K bar HPR in this bone. And it is obvious that this K bar measures the amount of Ricci curvature lying below n-1h in the LP sense. Note here, in all this talk, the K bar, there is an average of the volume. And maybe if you're familiar with Peterson and Wei's work, you will know that their K has not this bar and not the average the volume here. It is obvious if the Ricci curvature has lower bound n-1h, then K bar is always 0. And if it has the lower bound n-1h and minus delta, then K bar HPR is not bigger than delta. And let's say this K bar, it has 3 invariant H, P, and R. Usually we know H is given. It's the lower bound of the Ricci curvature. We want to know if it is. And the P, we often assume it is bigger than n/2. And there is R. R is maybe different one, maybe give different. So we will say if we fixed some R, then for each R1 that big than R, then K bar HPR has an upper bound delta, will implies on the bigger ball R1, the K bar HPR1 has also an upper bound. So if we assume K bar HPR, then we in fact have all the bound for K bar HPR1, where R1 is bigger than R. And for the small r, which is not smaller than the big R, usually we will rescue this manifold with R-1. Then the K bar on the rescued metric has lower bound compared with 0, and P and rescued the ball's radius 1, it has an upper bound which is also made very small. So from this page, we know that if we assume 1 R. Then for big R, we also know it's upper bound. And for small r, if we rescale the metric, it has also an upper bound. So in the following, we always assume r is 1. And, for the integral risk, for the manifold with integral Ricci curvature bound, the Laplace comparison estimate and the relative volume comparison has been proved. For the Laplace comparison estimate, if we assume psi is a maximal of delta r minus delta hr, where delta hr is the one in the space form with constant h sectional curvature. And we know if the manifold has Ricci curvature lower bound n minus 1h, then psi is always 0. And if the curvature, the Ricci curvature has not the lower bound n minus 1h, then Peterson way and Aubrey also, they derive that the psi can be bound by k bar HPR. So this is kind of Laplace comparison estimate. And for the relative volume comparison, same one, I'm writing the following form from me and Wei's work and not from Peterson way, because this form is more simple and useful in the following. So I write in the following relative volume comparison. We can see that this relative volume comparison is very similar with the one for manifold with Ricci curvature lower bound. Just have a term EC delta, and there is also a character here. And if delta is zero, then this one is just 1. So it is the relative volume comparison as the Ricci curvature has lower bound. Now let's say the main result of this talk is it's about the almost rigidity structure. As we know.
Sorry, could I ask a question?
Okay.
Okay. Could you give me an idea? So I'm trying to understand how much more general integral Ricci curvature bound is compared to pointwise. Is there some example I should have in mind which has the integral bound but not the pointwise bound, or what is the? Or could you just give me an idea how much more general is this setup? What is your opinion?
The example, maybe I thought maybe you can consider two form you want to pinch them, and in there, if they want to pinch the boundary there may not very good, and you may not control the Ricci curvature lower bound just as n minus 1h or some, but you can control the integral, especially if the boundary is, since its volume is very small, you may not smooth so well, such that the Ricci curvature has a lower bound, but you can make it has integral Ricci curvature bound.
So are you like a dumbbell? Is that what you're? I'm not sure if I understood the example. Is it?
I'm talk is not exactly example, just one case. If you may use integral Ricci curvature, more powerful, because sometimes you want to glue some two body together, and their boundary may not very well, and to make they have integral Ricci curvature is much easier than to make them has a lower Ricci curvature bound.
I see. Okay,
But
good.
I'm not. I can just tell you an example that which has just exactly integral Ricci curvature lower bound, but not has in the Ricci curvature lower bound. There's no example just in my brain now.
Right. It's not a precise question, but thank you. That helps. Thank you.
Okay. Now let's just see the result about almost the rigidity structure. As we know, Cheeger-Colding has proved for manifold with Ricci curvature lower bound, they have derived the almost splitting theorem and almost the metrical cone structure there. And we can show here that for manifold with Ricci curvature integral Ricci curvature bound here satisfies K bar HP1 is not bigger than delta, and delta is can be bound by a character depends on N, H, and P. If K bar is small enough, then the almost splitting theorem also holds for manifold with integral Ricci curvature bound. Note that compare with the one with Cheeger-Colding's almost splitting theorem, we assume the point, the distance between point QL has an upper bound delta minus minimal. They are just apart here. This is different, and the almost splitting theorem says that if there's a 2 point, they has distance L, and you can show that for any point that is close to the line between these 2 points, there's a ball around X, such that the ball has a structure just like a split, just like a product structure. The almost splitting theorem says that. And the almost metrical cone theorem says that if the volume comparison, relative volume comparison is almost holds, which we see almost holds because we have proved the relative volume comparison, we know the volume BBX over volume BBH is bigger than 1 and minus psi, which is very small, and with the sphere Bose volume ratio. And if we assume it is not bigger than 1 plus epsilon and the volume sphere ratio, then the ball has an almost well product structure. This is almost cone theorem says. And compared with Cheeger-Colding's theorem, in the almost volume cone condition there is for the annulus. And you can see that in all theorem, we assume the ball and the sphere ball. Why we state the form like this, use this condition 5, not a condition like 6. We will say it in the following, because maybe we can say it before, because we assume K bar, which is always average the volume over a ball, but not an annulus. So we assume of a condition like the 1 in 5 and not 6. And for the non-collapsing case, Peterson and Wei and Qian and Zhang, they also proved the almost splitting theorem and almost cone structure there. And the theorem here is for the collapsing case is also hold. If we consider the limit space of a sequence of complete n manifolds with k bar I goes 0, then we can also derive the integral Ricci limit space x d nu, where the nu is the measure, the limit of the renormalized measure. If we consider a limit space, we can see the splitting theorem holds there. And we can also prove some regularity of the limit space. In particular, we showed that there is some unique integer k such that the regular point whose tangent cone are isometric to Rk has full measure, just as Colding and neighbors result. And we can also use this result to derive that x d nu is an RCD n-1h n space. And you can see from Caterina's work, because this result mostly depends on their work. Caterina's work proves that x d nu is always a CD space. And if we assume the splitting theorem, then it is R CD space. So together with his work and this result, we know it is a RCD space. And I will not talk more about RCD. It is very complete, very far from my talk here. Let's see how to prove the result. The method is from Cheeger-Colding, because they have a very general results there. If you assume M has not, I write Ricci curvature has a lower bound here, but in fact, this condition can be replaced by segment inequality. That is, assume M satisfies segment inequality and the following two conditions. 1, 2, this is just the geometric condition, and this analysis condition, then it has a Y product structure. This geometric condition, this one, can be derived from relative volume comparison. And this 3, C0 estimate, C1 estimate, C2 estimate can be proved by the following tools, proved by Dai, Wei, and Zhang. They prove the maximal principle gradient estimate cutoff function. You use these tools, this analysis condition can always proved. And this one is from the relative volume comparison. So if you want to prove all results, we just need to prove this one, the segment inequality should be hold. So the main work, maybe I just done a little thing, very, very small thing, just the segment inequality here. let's see what is the segment inequality. Consider a function u defined on M, and let fu yz be the infimum of integral gamma u. Gamma is a minimal normal geodesic from y to z. And the Cheeger-Colding segment inequality says that if for a manifold with Ricci curvature lower bound, then the integral of f on a1 times a2, where a1, a2 be two measurable subset of one ball, then it can be bound by u's integral on a bigger ball, maybe 2r, b2rx. And note that there is two volume A1 and volume A2, and there also a small r here. And in all cases, we assume the integral Ricci curvature k bar. So we need two additional conditions. One is we should assume FUYZ has an upper bound C0 for some point, for each point YZ in B2RX times B2RX. And compare with the Cheeger-Colding segment inequality, we also have this additional term. This term is about this integral Ricci curvature bound here. And I think this term is naturally because we assume the k bars bound, not the Ricci curvature lower bound. So there must something added compared with their segment inequality. And this condition, FUYZ has upper bound C0, is assuming to prove this inequality. And we will see in the following that this condition is not, will make not any trouble to our proof. Because we compare with the segment inequality in Tianzang, note that in their work, they also prove two segment inequality there. The first one is consider U has zero upper bound, and they derive, we derive the similar, but there are compared to their work. This is useful for any F, and for collapsing case and non-collapsing case, it is always useful. And the second one, compare with their segment inequality, the different place is there. We can derive the volume, the right bound, the right side, we have the volume A1 plus volume A2. And in their work, they derive there is a space forms volume. They must have R, if they assume H is 0, then there is R n power, but not the volume of volume A1 and volume A2. Why this is useful? Because when we actually use the segment inequality, we should average the volume. And if we average the volume in the left side, there will be divide volume A1 times volume A2. And we divide volume A1 times volume A2 in the right side. We see that if we have the volume A1 plus volume A2, then we will divide 1 here. And we will divide 1 from the Hessian integral in the B to Rx, and 1 from the psi here. So we can control all the things. And if you have the segment inequality, just like Tianzang, there is a space form, then we have not the volume comparison like space form divide the volume A1. So so their segment inequality can only applied to non-collapsing case, and here we can apply it to collapsing case.
I asked a question here.
Okay.
So in the first inequality here, if you assume a C0 upper bound on U, and that implies the bound that you're assuming in the previous theorem, right? For the curly F.
If U has a C0 upper bound, then the U integral on an geodesic, it has an upper bound too.
Right. So what's the comparison? Like, what is this psi and how is it compared to your, is it just the same thing that's in your inequality or is it slightly different? This psi that shows up in
the first one, I want to say the first inequality, in our application, Tianzang's work, the inequality is enough. It can be applied to collapsing and non-collapsing case. The modification or improvement is from the second one about this blue colored words about the volume, and in their work it is about the space form volume. Like if you assume H is 0, there is R n power, not the volume A1 and A2.
Okay.
So the first one is not any improvement or not better, but the second one is useful.
Okay, thanks.
Thanks. Okay, so let's say the segment inequality in the integral ratio limit space. In the ratio limit space, the term K bar HP to R may go to 0. So there is no the term anymore. It is just like the one in Cheeger and Colding's segment inequality. Now let's see how to prove the segment inequality. The proof is just as one as Cheeger-Colding 2. Note that the most important part is here. In Cheeger-Colding, we know for Ricci curvature has lower bound. The volume element ratio, this is in the manifold, and AH is in the space form. Their ratio is a non-increasing for S. So by the non-increasing of this ratio, we can move the part AT theta to the integral part and derive there is a character C in HR. Is very directly from the non-increasing of the ratio. But for integral ratio curvature, there is no non-increasing of this volume element ratio. But we know that the volume element ratio satisfies this 7 inequality. So an observation is that if we consider for each S0 in T/2 and T, Then if we apply 7 here, we derive an inequality depends on S0. And this inequality holds for each S0, so we can take an infimum of this S0 between 2t/2 and t. And then we can move the term at theta to as theta in the integral part. This is the most important part. If we can derive this, then the other things is just like the Cheeger-Colding's proof. So this is only the observation, maybe some new or some new observation here. Just use this as how to move this at theta to the 1 in the integral. We just need the medial S0 and take the infimum, so it can be not bigger than any as theta. So we can do the same things here. And it is very simple, so I will omit it. Okay.
So can I? Where did the you required also an extra condition that f is bounded? Where did that appear?
The f has bound. Oh, okay. It's from here. You can see the where the C0 can come to the inequality.
I see.
You
And-
see it is integral, and this is f, and times this term. We want to this term to into 2 parts, and 1 we keep the u, and 1 we just use the f has C0 upper bound and just write it as the C0. Because this is psi, we know it can be bound by the k bar. So we want to f has upper bound C0. So this term just as can be bound by k bar. This term. Psi. Psi, we know it is the Laplace R minus Laplace HR, and compare with 0, we take the maximal. It can be bound by k bar HPR. So we know this term has an upper bound. And if f has not a C0 bound, then we cannot control this term. So the f's boundary is used here.
I see. Okay, thank you.
Now let's just say quickly about the how to prove the almost splitting theorem, and we will see why we use L. We should assume L has an upper bound by delta, and by this term. We know to prove almost splitting theorem, the most important thing is we should prove the excess estimate, which says that if the k bar has an upper bound delta, and the excess x has an upper bound epsilon, then for each y in a ball, in a small ball of x has an upper bound, this is the excess estimate. If this excess estimate is right, then as it is a normal way, like Cheeger-Colding, we can derive the C0, C1, and C2 estimate. So we just to see how to prove the excess estimate. In fact, here we use Dai, Wei, and Zhang's work, this L1 Haneke inequality. To control the EY, we just need to control the integral, the average integral of EY, because E is 2 Lipschitz, and by the L1 Haneke inequality, we just need to bound the delta EY. And we know delta EY, E is about the distance function. So there has 2 psi plus and psi minus. It is psi is just as before, the distance, the Laplace distance of D and the Laplace from the space form. So we want to control psi plus and psi minus. Note that psi is a distance function from Q plus or Q minus, and the ball, the center of the ball is X. So we should make the same. There is X, and we only can control a ball from Q, just the same from the psi. So there is a ball's comparison. Thus, we want to control psi, so we must assume L has some upper bound by delta, so we can control it. That's why we assume L has an upper bound like this form, because we want to control psi's integral. And we want to control psi's integral. We need to move the center of the ball X to the ball center at Q plus or minus. So there is we must control the L. That's the one compared with Cheeger-Colding's almost the splitting theorem, the different place. And to prove the almost symmetrical cone, the most important thing is to prove the Laplace estimate. That is, if you assume f tilde satisfies this function, and we want to see delta f tilde compared with delta f, the average integral have an bound small. We want to prove this Laplace comparison. And if we have the Laplace comparison, then the C1, C0, C2 is just like the one in Cheeger-Colding. So we see how to prove the Laplace comparison. We will see for the H is 0 case. If H is 0, then delta f tilde is just equal to n, and we know it has we can write like this. And here we want it has a lower bound, then we use the Laplace comparison here. We know for integral curvature, the Laplace comparison is for the psi. So we write a term, there is a psi. And we know psi can only have bound for ball BBX. So if we take an average here, this is a ball. If we just assume an annulus condition, then we will not know anything about the ball. So we may not control this term. So in our case, our almost metrical cone structure theorem, we assume form like the inequality 5 about the sphere ball and the ball ball's ratio because this time. And the other case is a similar thing. Okay, and any question about this part? Because maybe you have just forget what I say about the file condition. I just want to just talk about why we write a condition like this about the ball and the sphere comparison, but not like Cheeger-Colding's. They are in their paper, they write a form like the annulus and the sphere, because we said we want to control the psi with the ball, and the ball has must to the center, not to an annulus. This term. Okay. In the last part, let's say some further questions for integral Ricci curvature, which I'm very interested in the following questions. The first one is the generalized Maglo's lemma. Want to know if it is holds for the manifold with integral Ricci curvature. The generalized Maglo's lemma says that if the subgroup generated by short loops of the fundamental group is Cn nilpotent for manifold with integral Ricci curvature. We know this result have been proved for the sectional curvature has lower bound and for the Ricci curvature has lower bound by Kapowicz-Wilkin, but we don't know if it is holds for manifolds with integral Ricci curvature.
So I have a question about it because I don't know, because there is a Cn. What's the meaning of Cn nilpotent? I know the nilpotent in algebra, but can you explain?
Cn nilpotent is it has this subgroup has a nilpotent subgroup, and the index is not bigger than Cn.
Oh, you mean your sequence, the index should be has upper bound Cn? Okay.
Yes.
Okay.
And this is a very interesting question, and because it is very has many applications, especially this Cn bound, because by maybe Tao and other people I forgot, by their work they prove that for any metric space which says the doubling condition, then they always has a subgroup which is virtually nilpotent, but they have not an upper bound about the index. They just know it is virtually nilpotent. It contains a nilpotent subgroup with finite index, but the Cn is important here, so it is still open for integral Ricci curvature. And the second question may be about the topological about the limit space. We want to know if it is semi-local simply connected. We know for the Ricci limit space, this has just been proved by Wei and Pan for the non-collapsing case, and Jikang Wang for the collapsing case. So a natural question may be if we want to know if the integral Ricci limit space it has any topological property, if it is semi-locally similarly connected.
So I have another question. You know, I don't know this kind of stuff, but it's kind of interesting because I saw a lot of people write a lot paper. Can you explain me why this kind of semi-local simply connected is important? You know, I just interested in why there are some people are working on this. What's their goal? What do they want to get from this? Or if they prove this, what else can they derive from this?
Maybe it's the thing we see for the Ricci limit space.
Yeah.
The Ricci limit space has very close related with the space, the sequence, the manifold sequence, and in fact, the topology about the limit space, if there are any connection between the manifold and the limit space, is not clear to us, and it is hard to know. So that's why this result for the Ricci limit space is derived recently. And you want to know, it's just you want to know, even we know all this topological property about the limit space, what can we know about for the manifold? Because we focus on the manifold, not on the limit space. Maybe you want to know that.
Okay, so I have a question. If can the semi-local simple convex of the Ricci limit space can sort of help us to improve the regularity of the Ricci limit space or not? Or the topological information can help do some analysis?
Sorry. In fact, simply if you prove the semi-local similar connectedness, first we know it has a simply connected universal cover, and if you want to study the group action between, in fact, we want to know we always use some group action to study the connection between the manifold and the limited space. And if you know it is semi-local similarly connected, we know the universal cover is simply connected. And we have know the limited group is a Lie group, and the manifolds isometric group is also Lie group. So we can construct more close connections between the manifold and the limited, and we can more usefully, effectively use the group action between the fundamental group acting at the universal cover to study the sequence. Maybe I think this is useful there, but any applications maybe you can see for some fundamental group result about the space with Ricci curvature lower bound. They use this result and found it is very important there, maybe.
Oh, okay, thank you.
And the second question is about the quantitative maximal volume entropy rigidity. This question is the first one when I started to study the manifold with integral curvature, raised by Guofang Wei to me, and it is still open to us. So we will keep studying this question. It asks that for manifold with diameter with the upper bound and its volume entropy is almost the big one and has integral Ricci curvature, then if M is diffeomorphic and Gromov-Hausdorff to an hyperbolic manifold, this is a quantitative rigidity result for manifold. And I think this question is solved where it depends on the generalized Margulis lemma and so far we only can prove that if M is non-collapsing, then this result is right. And for the collapsing case, nothing is known about and no idea about why this quantitative maximum volume entropy rigidity holds. Since this is a question that leads me to study the integral Ricci curvature, and it is still open now, so I still very interested about this question. And
so I have another question. You know, so because I'm not familiar with this topic, what's K bar here? Or so what condition you are trying to generalize K bar? K bar is
because for the Ricci limit space, Ricci has a lower bound -n-1. The quantitative maximum volume entropy rigidity have been proved. Maybe you know Lazopy Wang's work about if a manifold has the maximal volume entropy n-1, then the manifold must be a hyperbolic manifold.
yeah.
Another question is if it is close to the n-1, then maybe it is close or diffeomorphic to a hyperbolic manifold, and it has been proved that it is right for a manifold with Ricci curvature lower bound. But for manifold with integral Ricci curvature bound, is that true? We believe it is true, and it have passed about 4 years, and we have no idea how to prove it.
Now your M is means compact. Okay.
Compact too, but generalized the curvature condition to this integral Ricci curvature.
Means this means that your Ricci curvature is almost in the sense of the integral greater than -1, right? That's what the definition of
Yes,
K bar.
yes. K bar is maybe it is not every point has lower bound.
Yeah, in the integral sense, okay.
You just can control that is not has -n-1, the point we can have a control, but we don't know the point is how many, and has the lower bound is what is the one. We just has the integral.
Did you ever try the scalar case? Just, you know, like what they do, you assume the sectional curvature or the bisectional curvature has something try to generalize this. It's just in scalar case.
No, we just prove for the non-collapsing case it is right, and for the collapsing case we know the M's universal cover is close to a hyperbolic manifold, but we don't know the hyperbolic manifold has a dimension n or k or some integer small, but we don't know anything about M. So we wanted to know if M is close and diffeomorphic to an hyperbolic manifold here.
Oh. No, I think that you can only answer any question on M, the universal cover of M. It's hard to say M because you can just every time you can just replace your statement by the quotient of M, right?
Yes.
Okay. Just it's enough to consider the universal cover, I think.
So we need something about its fundamental group, some information about the fundamental group of the manifold with integral Ricci curvature bound.
Actually, I read a paper kind of 3 years ago. I think someone tried to use the Hilbert transformation to do this kind of problem, unlike, you know, the work that you show here or some. I'm not sure, does it help you?
Oh, okay. transformation.
It's transform. Yeah, it's hard to, anyway, just read this many years. I tried this kind of problem before, but I just quit. Thank you. I have no any more question.
Okay, so that's all my talk. Thanks for everyone's attention.
Okay, thank you very much. Let's thank Lina again.
Actually, I have one more question.
Yes,
You know, I'm not familiar with this one, but just for Nina. So my question is that because the user thread is kind of the, you know, classic Cheeger-Colding method to try to punch your question, right? So I just hear someone told me it's kind of labor and Cheeger in, they have some new method can do something better, or probably can you share me, you know, what's the point of the Cheeger and the labor, the new method, or do you know that or not?
Their new method is to study the Riefenberg property about the limited space, to study the regularity about the Ricci limited space. Their new method is not here because you see all the result is a generalization for Cheeger-Colding's work in 1996
Okay.
or earlier, and their recent work I have not to study if it is true for integral Ricci curvature.
Okay.
I have a question, and please forgive me for the ignorance here. But could you describe what happens when k bar approaches this upper limit of delta? Like which estimates start to fail?
You want to know if k bar has an, assume k bar has an upper bound delta.
Or just
Or
as, yeah,
approach.
so in your estimates, you require that k bar is less than or equal to delta. And I just want to know what happens when k bar approaches delta, and sort of what falls apart when k bar is no longer bounded above by delta.
Oh, I know. You want to know if it maybe we assume k bar is equal to delta or equal 0. If k bar is 0, then it has Ricci curvature lower bound. And if it is not 0 and just delta, and not just delta, not 0, that's all. I think all the things we talk here, we just assume it has an upper bound delta, and this delta maybe just fixed delta, and this delta just smaller than a delta 0, which is only depends on NHP. Maybe this delta is just the delta 0 or smaller, whatever it is a delta. Then
that's exactly
delta is
sorry.
right here, and if it is equal 0, equal delta, then the delta is here.
Yeah, that's exactly, sorry, that's exactly what I wanted to know. So I guess I meant to say, what happens when your k bar approaches delta 0? Like, yeah, this nice constant that you have, which depends on the dimension and the curvature. I just want to know what goes wrong when k bar approaches that constant.
This constant is not precisely right, and
probably
we just
even don't know what's the optimal delta 0. Actually, I don't think you know it, right?
Yeah, we just know
Yeah,
there is one.
if you don't
but
know that, you
maybe
cannot
about
ask any further question about if delta equals to delta 0 or not, I think. Yeah.
Yeah, maybe that's the question you
I
want
see.
to know.
There's no as of yet. It's just a delta 0, which is bigger than. There's no formula for delta 0.
Yes.
Ah, okay, I understand. Thank you.
Yeah, I think that's a bug part of kind of this kind of technique. You always say there is this or something, but you don't know what's it.
It is really, it is precisely. We don't know.
I see. Is there hope for calculating it? And sort of, is there? Yeah, I guess. Sorry. Anyway, thank you very much for answering my question. I don't. Yeah.
This one is from the relative volume comparisons we prove, and maybe you can calculate from the relative volume comparison there.
So it makes sure this delta naught makes sure that the relative volume comparison holds. Is that sort of its function?
Yeah. In fact, we want to provide the doubling property and other things. We will, if we want to one property, we will assume a delta, and each delta depends on NHP. So we will say we always can find a delta 0, but if this delta 0 is the optimum one, or we don't know.
But it's not like that. Delta 0, it could be very large. Is it finite? Is it an infinite?
It is, in fact, it is very small. In fact, we want to compare all the things with Ricci has a lower bound. If Ricci curvature has a lower bound, then K bar is 0. We want it is very close to the case that Ricci has lower bound, so it is very close to 0. In fact, it is very small, I think.
Okay, thank you very much. Thank you.
All right, so in the interest of keeping to our schedule, let's thank Lina again for a very nice talk and nice answers to all of our questions. Thank you.
Thanks all your questions.
Okay, so let's just take a 2-minute break and return for the next talk. Yeah, in a couple of minutes. All right. See you soon. let's begin again. We're very happy to have Bozu from University of Minnesota to tell us about geometry of positive scalar curvature on complete manifolds. Thank you.
Okay, so let's get started. So first of all, let's thank for Brian who sent me an email to ask me to give a talk to share my work here. So actually I found his email in my spam after 3 or 4 days. So I'm glad I found his email. Okay, so today my topic is the geometry of the positive scalar curvature on complete manifolds. So actually I'm a graduate student at the University of Minnesota. So over the past 5 years, I'm kind of interested in the topic of the positive scalar curvature. I tried many problems, but like the other people, I quit a lot, and finally I get something from there. So, okay. So my topic includes kind of 3 parts. First I will, kind of introduce some interesting questions and conjectures to motivate you guys, and then I'll, share some partial result what I obtained, and finally, probably, I just right here, I will try to give less proof because whenever I show the proof, the people will feel it's boring. Okay, so let's get started. So the definition of the scalar curvature here, we will not follow the standard textbook. So we will say, okay, CUMN is a complete Riemann manifold. BPR is the geodesic ball of radius R and center at P. Just in this manifold, it's kind of geodesic ball center at P of radius R. And then we know the volume of the geodesic ball can be written as omega n. What's omega n? Omega n is the volume of the n sphere in Euclidean space. It's kind of the the volume of the unit ball in Euclidean space. This part is just the volume of the Euclidean ball of radius R. And then this is the volume of the Euclidean ball times this term, this chunk. And then from this, we define this number as a scalar curvature. From this perspective, you can say the scalar curvature is just, describing the deviation of the volume compared to the model of Euclidean space. So this is kind of, very, simple definition or, precise definition, but it's hard to use this definition, So, okay, why I use this? Because there is a kind of conjecture. Many people try to, propose this, but not many progress. So there is a conjecture just motivated by this definition. You can find this. I think there is a mathematician called Arin. So let me write it. He kind of in 1980s try to figure out try to punch this kind of problem. A Green, and he had a book. It's called The Tubes, and then in that, and he read a paper, and I think in ACTA, and try to punch this kind of problem, right? And okay, and then he said, okay, if the volume of the manifold is always equals to the Euclidean volume, and for any p, there is a small r makes this right, and then they just conjecture the manifold is flat, right? You compare the definition, this is kind of very reasonable, right? Yes, for some cases, people already knew it. For example, if n equals to 3 and n equals to 4, now it's known. And for n greater than 5, it remains open. So it's kind of, for this kind of question, I just think it's interesting, to my understanding, this kind of question, if you can, from that definition, we know the scalar curvature is kind of very flexible. If you can prove or in some condition prove this, at least you will connect the local scalar curvature information to the global. So that's why I, propose this here. Try to interesting you guys. So about the scalar curvature, I think, I think all of us here probably studied the differential geometry. So the curvature study is kind of a big topic over the past 40 years. Like Lina said, the Ricci curvature has, a bigger progress. And of course, more for the second curvature, more result, the pinch theorem has been obtained. And then, but for the scalar curvature, it's still quite open. Many problems are remains conjecture. So for the scalar curvature, the study of the scalar curvature in general, we just, I have a kind of, classification for my own study. So in general, it's got, okay, the existence of the topology of the scalar curvature. So in general, there are two kind of techniques. The one is called a minimal surface technique. And I think this is initiated by Sun and Yao. And recently on this field, Gromov is kind of popularized the mu bubble. And it's still, even, it's kind of fancy, but it's not that new. It's still the minimal surface. The only, I think I cannot say the only, the advantage is that, okay, sometimes it's hard to get the minimal surface. But, if you consider mu bubble, and then sometimes you can catch up a hypersurface, it helps. But all the other parts, I think, in the technique level, nothing new. And then the second one is called the direct operator. I think for me, even I studied the geometric analysis, I think it's in the field of the direct operators, they have, in a topological sense, they have much more aggressive, where I think probably the result is more beautiful than what obtained in geometry, or in differential geometry. I think a direct operator is initiated by Gromov and Lawson, right? And then also recently Gromov write many kind of the lecture notes, try to promote the two methods. I think that recently Hank and Guoliang Yu and Zhizang Xie and Jianmin, and they have some, I think, a very successful application to apply, solve some conjectures, So anyway, both, method has its own advantage and disadvantage. Many people try to connect the method. Also, okay, so the second part is about the metric structure of positive scalar curvature. I think it's probably sometimes, I'm more interested in this part. I try to understand the metric structure and incorporate, I say the size, or I can call it the Lipschitz environment. If you look at this definition, you can say, okay, sometimes the Lipschitz constant is, in the Lipschitz sense, it's to some sense, okay, if you consider Lipschitz environment, it's enough to help understand the scalar curvature, just perspective, not the precise theorem. And then, so there are many notations try to, Gromov also introduced many kind of sizes, quantity to understand the positive scalar. For this field, I think the most successful for me, because they have rigidity, that's the reason. I think the key area is the most successful for me, okay. And then the third one is about Novikov conjecture and scalar curvature. This part is kind of also, I think, initiated by, how to say, Lasgese. I think he just got the Wilf Prize. I think he proposed an analytical method to understand the scalar curvature under the Novikov conjecture. Okay, from recently, kind of, I'm studying this kind of part. Okay, so what I did, or what I interested in before, is kind of from the geometry. I think what we know, the positive curvature will imply the space curved, right? So this is kind of, the basic intuition for me. So let's record two classical results. So first one is the classical, result on the diameter theorem. So if M complete Riemann manifold, which is greater than the standard space, and then if the diameter is less or equal to pi, the diameter is always less or equal to pi, and the equality holds if and only if this is a standard for a standard sphere. So this one is quite, famous, right? But the second one, it's not that famous. So maximal conjugate radius, or sometimes call it a maximal injective radius. So if M is a complete manifold with scalar curvature is greater than the standard space, we assume the manifold is closed or just, compact without boundary. Okay, we have the injective radius is less than the conjugate radius, and it is less than pi, and the equality holds if and only if this is a standard sphere. So actually in this field, probably 2 weeks ago, Gromov also read a paper, try to generalize this. So my question here is kind of, that's my research experience. So what's the generation above theorem? So okay. So let's universal width is a generalization of kind of the diameter. So let me say, so I think the universal width was introduced in Riemann geometry by Gromov in 1918. I think, and it has a lot of, interesting conjecture or important conjecture related to this concept. So actually this concept is from the topology and introduced in math by Ricci in 1920s. So let Mn be a Riemann manifold. K is just a K polyhedron. P could be compact or non-compact. If it is non-compact, the P has to be local finite. Okay, so locally the dimension is finite. And then we define the universal width K. So what's the meaning of universal width K? So don't look at the definition, just I will explain. So we have M, and then we have P. This is N dimension. This is K, and then we always, in general, we assume K is less than N, less or equal to N, because if K is great, this always can be 0. This can be always 0. So, and then this definition is that universal width means that, okay, we try the F, and then we try to measure the diameter of the fiber. So it's kind of, this quantity is measured, how is this manifold close to a lower dimension manifold? So that's the universal width. For example, if K is 0, so you map your manifold to a point, and then you can say the fiber is a point, is just a whole M, that's a diameter, right? So if K is one dimension, the fiber, generically, you can say, we can always assume F is a most, good function or Morse function, and then this is N minus dimension space. And you can say, okay, if this diameter is small, you can say, okay, this N dimension manifold is just, close to 1 dimension space. Okay, so that's kind of the universal width. So it's kind of the universal width is measuring how your space is close to a lower dimension space. Okay, so for the universal width, if this is the kind of directly applicate result from the definition, we get a sequence. If the index K is greater, and then the universal width will be smaller. You may say, why not write the universal width N? Because the universal width N is always 0 because it is equal to the dimension. This definition can be used in metric space, not only on Riemann manifold. So it's kind of, we give a sequence. I think for this part, Gromov also has many conjectures about the size. The basic question, okay, can we use for example, here you got N numbers, right? Can we use these N numbers to characterize the manifold? So I think a perma has a result in 98. If this is this, they can say we multiply them together. Universal with you multiply them together. I think this is equivalent to the volume of the manifold for compact manifold. Okay, so I think that's what the perma got, you know. So it's kind of universe to some sense they can control the volume. But you know, the question is that can we, you know, replace your scalar curvature by Ricci is still unknown. Okay, and then related to the universal width, and Gromov also introduced the macroscopic dimension. So, and then we know, you know, for this time, always M is long compact. Otherwise, okay, it's hard to say. If the universal width is, you know, universal width is less than 0, less than infinity, and then we take the smallest, okay. You may say, how do I do this? Can we always get a K? Like I said, if the dimension greater, if K is greater than dimension, this is always than 0, right? It's kind of, you just from the, go down to the earth and then you find the smallest K. So I give you a feeling, what's this? So the basic one is that, okay, look at this, right? So you can say, what's the micro dimension of this? So we can always project this to Rn plus 1 and plus 2, and then you look at the fiber. This fiber is finite because of this. In this kind of sense, the microscopic dimension is n minus 2. Oh, it's kind of, you know, this kind of problem in larger scale. What's the dimension of the long compact part? To some sense, that's not a definition. Okay. Okay. So let's look at this, the Gromov conjecture. So the first one is called the universal width version. Okay, so if M is a complete long compact manifold, if scalar curvature is greater or equal to the standard manifold, and then there should be existence Cn, and then the universal n minus 2 of M is less than Cn, sorry. So what's this conjecture try to tell us? So this kind of tell us any complete manifold with strictly positive scalar curvature has a dimension n minus 2 in large scale. So that's a model. I think in many places, Gromov said, okay, that's a model. He said that's the model to motivate, you know, him. So it's kind of, you know, that's a model that, you know, it's n minus 2. And then so the question is currently, okay, how much, you know, what kind of manifold do we need to support the positive scalar curvature? To some sense, whenever you want to a manifold has a positive scalar curvature, actually you have 2 dimension or 2 dimension. In some kind of 2-dimension space, the manifold has to be curved. And then in this kind of sense, the 2 dimension has to be curved. And then probably the other n minus 2 dimension can be very flexible. You know, this is kind of the philosophy. And then, you know, someone doesn't like this kind of problem, you know, just say, okay, I like the topology, I give her fine 0, 1. Okay, so if M is a complete manifold with Ricci is greater than this one, and then the micro dimension is n minus 2. Actually, even for n minus 1, it is unknown up to now. In general dimension, it's still unknown. Okay, for the n dimension. Probably you may say, why the people ask kind of this kind of question? Actually, it has, you know, is related to some deep other question. So also it's kind of the philosophy for this kind of question is, okay, so because, you know, many techniques, you know, tells us, you know, 2-dimension space, is kind of in 2-dimension, the manifold has to be curved, and then how to describe this kind of problem. And then the universal width verse conjecture is kind of a good formulation for that intuition. Okay. So, and also you can say the universal width, this is a conjecture, right? The universal width is less than, say, that's conjecture. And also we can ask this. So if complete non-compact manifold scalar curvature is greater than the standard space, can we prove the the injective radius is less than pi? Compared to the previous page, let's look at this. So this green theorem, I think this proof in 1984, okay, it is only for closed manifold. So also the question is, can we have a non-compact version? Can we prove the injective radius less than pi? Probably by my experience, even you prove this, okay, you can say this kind of problem is interesting because it's nice, right? Answer kind of question. Unlike the universal width, if you can solve the universal width even for n-2, probably you are right, that's a bigger contribution. Okay. This one, you prove this, I can say, okay, it's nice, but I cannot find other application. Probably maybe other people can. So it's still interesting. I think like what I said 2 weeks ago, I thought that's kind of problem probably 2 years and no progress. Gromov also write a paper, try to propose this kind of question. And then, okay, he said, okay, let's deal with some special case, spin and some manifold over torus, or they can always get something, okay, by the direct operator. But for general, nobody knows. Okay, of course, Gromov proposed a general version one that I never saw, but I just focus on this. No progress. So let's come back to this question, universal width. It's kind of interesting. So universal width conjecture, not this one, not the injective radius conjecture, the universal width conjecture holds as n equals to 3, remains open as n equals to 4. Okay. Actually, if you read the literature, I think universal width, it's hard to say. I think in the, if you check the Gromov's paper, I think up to now, for this case, I think the people only know compact case. The people only know compact case. Okay. And for non-compact case, I think in Gromov's lecture note for lectures on scalar curvature, there's still something on the H1 is trivial, is 0. Anyway, I didn't say any literature to deal with the non-compact case without any topological something. But for the higher dimension, it's quite open. Nobody knows. I think many people try to solve this. Of course, let me look at a 3-dimensional case. Just something classic. Any closed 3 manifold with positive scalar curvature are the collected sum of this and this and this. It's kind of some called aspherical, right? By their spherical. Sorry, wrong. So the main reason is I'm interested in this part because I know this kind of conjecture many years ago and then tried to read and finally I came here. So I think it's a big conjecture, right? Any closed spherical manifold admits no metric with positive scalar curvature. And then Gromov tried to accomplish this conjecture following this kind of path, the universal width version. But up to now, it's not that successful. Actually now, when I first read this paper, I read Gromov's paper, he said, Yao and Shen already proved this for 4 dimensions, but actually not, big mathematicians always claim they prove something, but no details. But in recent COSC and Li, they use a mu bubble, and then they prove the conjecture for dimension 4, and then Gromov proved the 5-dimension case. but for the other dimension, it's still unknown. Actually, someone, if this assume, for example, unrelated is, in the direct opposite method, some people, okay, say, if we assume the manifold is a spherical manifold and the pi 1 is hyperbolic, and then they say, okay, the Novikov conjecture holds, and then they can, okay, choose, derive, there is no scalar curvature on this. So there are many partial results, especially, not in geometric analysis field, in kind of direct opposite method, non-commutative geometry field. They have someone, whenever it's kind of to some path, they can prove the Novikov conjecture. This kind of theorem is a trivial corollary. Now it's trivial corollary of that conjecture. So that's why in non-commutative geometry, they are also interested in the scalar curvature now, because that's a corollary of their big conjecture. Okay, but for higher dimension, because they use the minimal surface, take leaks or the Mill bubbles, take leaks, whenever they go to high dimensional space, there is no Gauss-Play theorem. It's hard to, it's kind of the trick cannot be played again. That's the reason. It's still far away from the theory, by my understanding. So many other quantities is kind of the quite a size quantity. It's not me introduced this. I think a lot of goods. ICM and lecture note, and he introduced and gave the name for this kind of quantity, systole and field radius, and this is what's called the radius, sphere radius K area. They give them a uniform name. It's called the size. So many research paper related to this content, but all the philosophy is kind of try to punch this kind of conjecture, Rules-Weiss conjecture. Okay, in general, why I say, okay, for the key area, it has a successful result because they assume the speed, because the speed, the direct operator, like the Buckler formula, it's useful in geometric analysis. So, and then, parallel to the scalar curvature, if you look at Ricci flow, it is parallel to mean curvature flow, right? Many parallel results has been obtained. And also you can understand the domain of the strictly positive mean curvature, strictly mean curvature domain in Rn. So unlike the minimal surface, it's the famous many mathematicians are trying to figure out. Actually, a basic question is that how do we classify the mean convex domain, strictly mean convex domain, a strictly positive mean convex domain in Rn? It's still quite open. I think there is a Gromov read a paper, try to push this kind of question. I think the lemma is called the mean curvature. Scalar curvature? Oh no, mean curvature in the light of scalar curvature. Anyway, I just, I think it's interesting. I did something, but still far away from, Gromov's ambition. So anyway, finally, I would say, this kind of problem is interesting, but we have a very poor understanding of this kind of question. It's hard for whenever we talk about a scalar curvature, many probably is hard. Okay, Ricci is greater than 0, we can say the pi 1, right? Scalar curvature cannot imply any pi 1 information, even, okay, pi 1 help to understand this. But actually, the basic philosophy is that if use pi 1 is too big, what do you mean too big or large? It's for that kind of manifold, it's hard to admit a metric with positive scalar curvature. Okay, just to some sense. So, and also this spherical manifold is kind of, just pi 1, all the pi k, sorry, I forgot. For k is greater than 0 is 0. Greater than or equal to 2, only no pi 1, but a pi 1 cannot 2 be is too big, for example, hyperbolic, right? Pi 1 is big and no scalar curvature. Many things are in the conjectural level. So let's kind of come down to earth. Something is possible to have some progress in short time. The first one is called a Yao conjecture. This is many people in geometric analysis try to figure out this, but the progress, this one is still unknown in 3 dimensions. So complete, non-compact manifold, Ricci is non-negative. Okay, Yao conjecture this. Can we have this? Right? You know, ask my advisor why Yao asked this. They told me I don't know. Anyway, but you know, if you put it on my under context, it's kind of, if you, okay, let's look at the second one, and then you say, okay, from the Gromov perspective, okay, you can find a reason to believe it's right. Okay. So Gromov conjecture is scalar curvature is greater than 0, Ricci is non-negative, and then the volume is less than n minus 2. Actually, I think we all know that if Ricci is non-negative, the maximum volume growth is Euclidean volume growth, right? But the question is that actually, if you have a little bit of positive information on the curvature, can your manifold can express the in n dimension? Does really the manifold has 2-dimension collapsed? No, cannot do that. To some sense, 2-dimension curved cannot spread fully or in n dimension. That's kind of, it's same as some people, Ricci, if the people understand it, Ricci, say, okay, you are at some trick, play the trick. Now, whenever, can you really understand the positive, how the positive scalar curvature implies or affects the volume growth? If you can prove this, you can say, okay, the harmonic function, the dimension of the linear growth, the harmonic function with the linear growth is the dimension of the harmonic function with linear growth is less than n minus 1. This kind of, has some kind of, dimension control on the harmonic functions. If you look at this, you can say, yeah, no, Gromov's conjecture is kind of, corollary of the Yao's conjecture to some sense, if you don't care about the constant Cn. Okay. So it's kind of, I'm trying to do this kind of problem during my graduate study here. So actually there's some progress. First of all, I have said, without consideration on the constant Cn, Gromov's conjecture is weaker than Yao's conjecture. In fact, sometimes probably, Gromov is more ambitious. Probably this is not all right. Does really has a uniform Cn? I don't know. My bias, I don't think there is a Cn. Probably, the n minus 1 growth is possible. Probably I'm wrong. I just, probably there is no uniform Cn. Okay. Okay, and then Petroni, okay. He proved, okay, if you should read the section curvature is greater than 0. Oh, actually, Yao's conjecture is right with a stronger condition. That's right. And there is a uniform constant. Okay, it means that in that sense, you can say with a stronger Cn, you don't have to take the info because we don't know this is uniform by Yao's conjecture. Actually, if you read some paper in 1980s, this kind of interesting because at that time, many people are trying to understand the curvature decay, and then it's kind of, the curvature decay 2 plus alpha. If the alpha is greater than or greater than 0, this manifold is with Ricci or second curvature is greater than 0. The alpha is greater than 0. Your manifold is kind of homomorphism to diffeomorphism to Rn, or even in Kähler case, this alpha cannot be 0 for their result. It's critical, alpha, 2. This 2 is a critical index or power. Many things kind of, related to the classical result. Okay. And then also Labor and John also try to answer this question and try to approach Yale's problem. Okay. And they also, they also propose some version question. If switch curvature is like this, volume is long collapse. They always similar volume collapse because they take leaks, cannot deal with this. I talked to John, seems that they don't know how to deal with any long collapse case. Okay, and then there exists a constant C such that this. Anyway, this kind of question, there are many kind of questions related to scalar curvature. So, and then you can say, okay, what I am doing.
Okay,
So
I
first,
have a question
Yeah,
here.
yeah.
You have just mentioned the neighbors this
Yeah.
result. Is they
Yeah.
prove that SC has a power alpha that is smaller than
Yes.
1?
They proved this when if this scalar curvature and this power is alpha is less than 1, and then this is always less than say alpha is less than this say depends on alpha is less than 1. They try to improve this alpha to 1, but they cannot.
They
Clear?
try to, but I have not seen the result about this
Oh, I
alpha.
talked to John. I talked to John because I have overlap with him in university, and I talked to him, and he just said, "Okay, that's trivial because just 1 page. You can." They said they just derived from their result in 1 page. That's why they didn't write it out.
Okay.
Yeah, because they think it's too easy by their result. Okay. Anyway, that's what he told me. It's a lot of what I want to say. It's easy. Okay. Okay. So they try to improve this to alpha. Oh, it's kind of, by their result, they can say, okay, the volume of BPR is because if we know this, because I plan to say this later, since you asked me, okay, I say it here. So this is kind of n minus 2 plus alpha. They try to make alpha to be 0. Actually, when we talk to them, they don't know there's a Gromov conjecture. Even, I told them, okay, they cannot improve this alpha, to improve this alpha. No, can I say cannot prove this for alpha equals to 0. And they still don't know how to prove the Gromov conjecture. Actually, there are some essential difficulty for this kind of question, So, and then actually, I'm trying to understand this part. Whenever we assume there's a pole in 3-dimensional case and Ricci is non-negative, we can kind of derive this kind of formula. Actually, this is not that hard, I just have a basic observation and then we derive this. I can say almost trivial. Whenever you can do something, it's trivial. Okay.
What does it mean of pole? What does pole mean here?
Pole, this kind of language is not famous now. It was famous in 40 years ago. Pole means that at one point, your exponential map, just 1 point. Exponential map is a diffeomorphism from the TPN to M, just like this. Your shape like this. This is a pole, you can say. Is it clear?
Okay, yeah, it's like like a soul or something.
Yeah. So kind of like, but it's usually the pole. In 1980s, the people do a lot of questions about this kind of problem. And in recent 20 years, this notation is not that famous. Okay. So whenever it is a pole, and this is always right there, your uniform constant, just because I have the observation, this one, I just use this. Okay, and Ricci is non-negative. And we assume C is any number which is less than the conjugate radius. And just a number, it's just okay, injective radius because either understand. Okay, and then this curvature has kind of this and this. You can say from this, if you forgot a pi, this kind of constant, there is a c squared in the denominator. Right, probably this, if you take c as half, right, this is kind of 1/r squared. This is the maximum volume growth. This is more kind of, implies Yau's conjecture. But you cannot say, okay, let's say equals to this and take c as, because c cannot be infinity. Because if conjugate is infinity, you have the assumption Ricci curvature is non-negative and this manifold is Euclidean space. So actually you cannot say from this you can go furthermore, you can go furthermore, but the question becomes trivial. You didn't make any contribution. Okay, that's why just observation at the first beginning. Okay, I find this and then I try to do Yau's conjecture, but it's not. Okay, finally, this motivates us to do this. Actually, this is not that big deal, just some observation. So this is kind of Yau's conjecture. And also, like what I said, if you assume Ricci is non-negative, the conjugate radius is less than pi. But the injective radius conjecture without assumption on the Ricci, this without the Ricci. I just say, okay, if from Ricci, that's possibly right. Just give me evidence. Okay, this could be right. And also Gromov from other perspective. Okay, it's also could be right, injective radius conjecture. And finally, for the Gromov conjecture, we assume Ricci is non-negative and the second curvature is non-negative. Actually, there is a uniform constant and Cn such that the volume is this. We cannot prove the n minus 2 without any assumption. You can prove this. At the beginning, I cannot prove there is a uniform constant, but finally, okay, we can prove there is a uniform constant by other method. Okay, if you look at my paper on archive, for that one, I cannot get a uniform constant Cn. But now I can say the uniform constant Cn. But for the injective radius is kind of, I call this is injective radius long collapse. Probably for the people who study the Cheeger-Colding theory. Okay, this is the condition is too strong. Oh yes, it's too strong. It depends what do you care about. Oh, sorry. Okay. So it's strong because we know this is say. If we have injective radius, we know this is C alpha convergence. Yeah, it's good. We know this is a manifold, right? But so what if you care about the scalar curvature? Even this is C alpha, this is a manifold. Can you generalize the scalar curvature on this kind of manifold? Actually not. Even when I give you this strong condition, can you do some scalar curvature analysis on the limited space? That's a question, depends what you care about. Even in this case, okay, I can say Gromov conjecture is right. Probably it's too strong for someone, For me, I think, okay, just interesting, because I try to generalize the scalar curvature. A big topic in this field, in scalar curvature, how can we generalize this scalar curvature? Like what I said for the size, whenever you can prove some size scalar curvature, because this size property or quantity are limited environment. Whenever you can say, okay, compared to the model, the size is less than the size of the model. And then you can use this kind of quantity, replace the scalar curvature. And then you can do scalar curvature, sort of scalar curvature in your singular space. That's kind of a bigger project. I think now, they are also in their methods try to, generalize in their work. Actually, it's not that successful. And also I talked to Liu Gang, and he told me, okay, in Keller case, long collapse case, actually they can introduce the scalar curvature because at that time they have kind of the potential because the Keller is always special. And then they can say, they can have better understand the singularity, because that's algebraic variety codimension less than 2. In general case, if you care about a real Riemannian manifold, it's hard, to understand the scalar curvature on the Ricci limiting space. Actually, injective radius is like this. But you couldn't ask me, why can you get this? Why not a volume collapse? Because this is injective radius collapse. Because actually, I only use one point about the Cheeger-Colding theory, because I need to use the limited space is a manifold. That's the only place I used. Whenever you can prove the Ricci limited space, the Ricci limited space is a manifold, topological manifold enough, and then my argument will work. So, probably you guys are familiar with this, right? Sometimes more familiar than me. And for 3-dimensional case, actually the volume is, if we stream a volume line collapse, it works. We can prove this. Actually, I prove this. Actually, after I prove this, my advisor, he just completely solve this problem. They can prove without this is right. Just different method with, different flavor. Okay. So it's kind of in 3-dimensional case, and the volume is long class. If you compare this is, if you compare the job of John and labor, to some sense, for this is greater than 6, I can improve their alpha to be 1, not the integral, just this one. So the only one is that I didn't analyze the scalar curvature on the Ricci limiting space. I am, try to use the Lipschitz invariant to avoid this difficulty. That's kind of, the trick that I used. And then finally, so I say, okay, if Ricci and scalar curvature is greater than 2 and a volume line collapse, actually in this case, your M is close to R. So it's kind of, my basic, picture in my mind is that Ricci is greater than 0, scalar curvature is positive. Actually, your manifold should be like this. That's why I thought this kind of problem should be right. It's kind of like this. It should be like this. Of course, I didn't say it's a pole like this. I should be like this, 1n. Or of course, you don't have to care about this case, right? It's trivial. The hard part is, can we do this? Because this is split, right? Whenever you have 2 ends, it's split. You have whenever it has 1 end, just like this. So, and then this kind of theorem is kind of say, okay, your manifold with this curvature condition just close to a line. So that's, it's kind of my geometrical intuition on this kind of problem. Okay, so this is kind of usual ways. Actually, like what I said, I will not give many proof, but I will tell you something that I think is interesting, probably maybe useful in the future. So there is a lemma, it's called a relative Bochner formula. So it's kind of, if we have a smooth manifold on M has no critical between A and B, no critical value in AB, and then we have the reach, this part. This is kind of, the interior part. This is the boundary part. What's H? H is the mean curvature. This is the mean curvature. What's G? G is the mean curvature squared minus the square of the segment fundamental form. So this kind of question is kind of, you convert the integral in the interior to the boundary part. I kind of use this to prove, the polar case, the Yao's question on the polar case. I just, I read the paper, they have this, and then I use this and derive them more. Actually, this is quite a standard argument. It's, nothing new. But I want to say this kind of is interesting, because, if you are familiar with Ricci curvature study, you always, because this part could be complicated, right? The interior of the manifold is annulus like that. The geometry of the manifold, it tells you, okay, to some sense, this integral doesn't depend on interior, it only depends on the main curvature. Okay. Okay. So actually, if Ricci is non-active, or Ricci flat, I don't know, in other case, it can be useful in some case. And then I will not show this because whenever you know this, the other part is trivial. Okay. So how do I prove the volume? How do I prove this? BP. Probably I still have 3 more minutes, right? Okay, and say n plus 1. How do I prove this one? So I just say, okay, Ricci is non-negative, scalar is this. Probably you may say, why do you assume this? Just a rescale details. You can still say greater than 2. Just for my proof, I just, after I fix my constant, I study in this way. I just say, okay, Ricci is greater than there. We know the volume is always less than omega n. Omega n is the volume of the unit sphere in Euclidean space. Whenever you assume the scalar curvature is greater than 0, oh, there is a gap. That's what I obtain. Whenever there is a gap, and then you can prove this. Actually, when I'm proving this, because I know if I can prove there is a gap, I think by who radar, I forgot time, anyway, that many years ago. And then whenever I prove this, this is kind of trivial. That's kind of, the class that I do this kind of problem. At the beginning, I asked many people, I asked John, okay, is this trivial? I say it could be right, but I don't know. There is a literature write this. People just think it's right, there is a gap, but how do we figure out? Finally, I use the kind of the, how to say, the toric bonds with recently to figure out this. I think this was proved by Gromov. I use a lot of Lipschitz invariant to avoid the difficulty that you meet in Ricci limit space to, get this work done. Whenever.
Can I ask? So what do torical bands have to do with this local volume lemma?
Okay. So this kind of, whenever, you can prove this, if you assume this not right, and then this BP1 will convert it to this BP1, right? Infinity. Because this is long collapse if it is close to omega n. And then this is a ball, you can take a toric bond in this, and then you pull back to this, just pull back, and then there is a bond for this one. And then why I changed this, the reason is, okay, I changed that, pull back, because when you pull back, the distance between the bond Tn minus 1 and A minus B, and then, the distance AB in this metric is close to this, because they are close hostile, right? Topology is the same. And then you can control this part, and then this can, okay, sorry, you can make this is bigger. No, sorry. So let me change another one. Don't use the toric bond because they are equivalent to each other. We can choose a cubic in this. We can choose it's easy to choose a cubic in Bn, right? And then because it's 0, we pull back the cubic in this one. The distance between the cubic, we can assume it's not that small because it's Euclidean space. And then you pull back the distance between the opposite. Sorry, I wrong. The distance between the opposite sides is not small in the limited space. You pull back to the manifold, it cannot be small because they are close to each other. But we have the scalar curvature is great. And then you get a contradiction. So that's the idea. actually, this cubic estimate is equivalent to the torque bound. Okay.
Yeah, makes sense. Thanks.
Okay, the tuition is quite simple whenever you have this observation. Okay. Okay. And then probably I will stop. The idea for the third one is the same. I think the only thing what I use is when I solve this three-dimensional case, I cannot do this. One another reason is that there is no kind of the torque bound for any dimension, or the cubic estimator. When I first figured out this problem, it's kind of this was done kind of 4 months ago. I think by Guo Liangyu, by Jianming Wang, Zhizhang Xie, and Guo Liangyu, they use a direct operator to solve Gromov conjecture, and then you can do any dimension. Otherwise, before that, I can only do the dimension within 7. Okay, sometimes take a leak. And then let me look at, in volume long collapse case. So I want to say if the volume is long collapse, and I want to prove the volume BPR and R limit U R goes infinity is less than infinity. How do you do that? Actually, the philosophy is the same. And then, like what I said, whenever you know the topological, the manifold is a topological space, all my argument will work. I use their result, and then because they prove the limited space is a topological manifold, and I use that, and then by contradiction, by the Cheeger-Colding splitting theory, we have this, we have this, we have this, and then there is one more lemma I prove is that okay, if we have a volume, actually I can by the lemma I can rule out this, and then by the total bound take league or cubic law, I can rule out this. And then finally, I proved that this is a linear growth. So it's kind of, I use the total bound, from the scalar curvature in this kind of context and prove it has a volume growth. Actually, I also tried the mu bubble take league, but I always have some difficulty to encounter. But anyway, it's hard. So anyway, finally, I would say is that, if we assume the injective radius is long collapse, just it has a lower bound, can we try to derive a scalar curvature in the Ricci limited space? I tried to figure out this for a long time, but I have no idea. And one reason that I'm not that very familiar with the Cheeger-Colding theorem. I just, for my use, I go to study something. Okay, I think I'm done. Okay, I'll stop here. So let me say, do you have any question?
Okay, yeah, let's thank Bo for very interesting talk. Thank you.
Okay.
Okay, yeah, so please, do we have any questions for Bo? So it's interesting. So is it accurate to say that a lot of what you were explaining in the last part of your talk, you use a Ricci lower bound to be able to take a limit, and then that allows you to use the torus band?
Yeah.
Yeah, that's an interesting idea. I haven't seen that before.
Yeah. I think that's I think I'm the first person to try to combine them together. It's not that a big deal, but that's what
it's important to, because the torus band inequality, it should be like, in my opinion, it should be similar to like Meyer's theorem or distance. Yeah, and so it should have implications for these sorts of questions, but people haven't we haven't seen
actually yet. I think Gromov never explains this, why he tried to propose this kind of torque bound,
because actually he is also trying to figure out the universal width. You know, universal width is just a special case for that torque bound. For general case, they don't know how to do it. That's why. You know, it's still under the universal width conjecture, but he never figured out in his paper, you know, explicitly.
Yeah.
Actually, I think probably your group, you know, are more familiar with, you know, kind of the convergence theorem, right? For a long time. So let me ask you guys a question because I don't know. I can say, so if for compact manifold, we assume the scalar curvature is non-negative, compact or closed without boundary, and then I assume the injective radius is greater than a uniform lower bound, has a uniform lower bound. What can you say about this class? I think, you know, because for somatic group, I think many of you have some experience with him. Did you ever thought about this kind of question?
This is related to the scalar compactness conjecture.
Yeah,
right?
yeah. Kind of like that.
You assume positive scalar curvature and in Surmounting's formulation, a min A bound, and that's open, right? But the sequence should converge to something with positive scalar curvature and have certain properties. But I don't know, I haven't thought about it with injective rays, but that's still a conjecture that's open.
Oh yeah, okay.
It should be that class should be well behaved.
Yeah, because injective radius, right?
Yeah, all of the interesting phenomena for a convergence happens when you have you know, splines, you know, thin cylinders and necks. So I don't know any I don't know what you can do with those assumptions, but I would expect you should have a very nice theory, more classical theory for that class of manifolds.
Yeah, that's
Good
why.
question.
But it's kind of, you know, I don't know where I get started.
Right. Yeah. That's exactly right. None of us do. Yeah. Okay. Yeah. Before we go into more informal discussion, does anyone have any other questions for Bo? Okay. So let's thank him again, and then maybe we can ask some more questions if we have them. Okay.
Okay.
Thank you. Thank you. Okay. And I can